Good day, welcome to a new thing. We've been talking a lot about the redox table and using voltages from it, and these voltages on the right here are numbers that tell us how willing is a certain substance to go through a reduction reaction. And it turns out these numbers that we give you here are arbitrary in a sense. All of these tell you how good is something at reducing compared to hydrogen. They had to pick someone or some substance on this list to be the standard, and then they compare everything else against it. Why did they pick hydrogen? I believe it's just because any chemistry lab in the world can make hydrogen if they want and can arrange to do this reaction by getting any acid and reacting it with anything beneath it, and there's plenty of substances down there, and producing hydrogen gas, which is not too hard to manage if you have a well-equipped lab. So they picked this as the standard, and then when you say that silver is 0.80 volts, you're saying silver is 0.80 volts better at reducing than hydrogen is. So this 0.80 doesn't have a real meaning by itself except to say that silver is 0.80 higher than hydrogen is. It's like if we picked one person in the world and gave everybody else's heights as I'm 10 centimeters taller than Mary, he's 2 centimeters shorter than Mary, she's exactly the same size as Mary. We could do that and Mary would be our height standard and we'd use her for everything. In this case, hydrogen is our reduction standard and we use it for everything. But what if we hadn't? These questions are about the hypothetical where we use some different standard. For instance, here they say, if the chlorine half reaction were assigned a reduction potential of 0, in other words, if chlorine were our standard, then what would be the potential for copper? So, looking at our table here, here is the chlorine half reaction, Cl2 plus 2 electrons to 2 chlorine. What if, for whatever reason, chemists decided they really liked chlorine and they wanted that to be our standard? And they made that 0. What would that do to the rest of the table? Well, to turn chlorine from the number it is in our book down to 0, we would obviously have to subtract minus 1.36 from it. If we were adjusting our table, we would go minus 1.36, and now chlorine is 0 and it's our standard. Well, if we did that with chlorine, we would do it with every other substance. So fluorine would drop by minus 1.36. New number would be positive 1.51 volts. And the lead acid reaction would go down by minus 1.36. So that would end up at 0.33. And so on, all the way down the line. They're asking about copper 2 right here, which is usually at 0.34 volts, but in the chlorine world, it would be 1.36 less, so it would be negative 1.02 volts. This wouldn't change how any batteries worked because the difference between two numbers would remain the same, but it would certainly change how their data book looked. So for this one, the reduction potential for copper 2 would be listed as minus 1.02. Not too bad? Not too bad, I hope. Let's see if we can do a bunch of those. Alright, so I got negative 1.02 volts for that one. Next one. If the aluminum reduction was our standard, if that was 0, let's just pause the question right there and take care of this. Here is the aluminum reduction. If that was 0, what would you do to get that reaction to 0? You'd have to increase it by 1.66. Fair enough. Well, if you're going to do that to aluminum, to be fair, you have to increase everybody by 1.66. So every other number on this table is going to get a plus 1.66 on it. Now, the one they are asking about in question 2 is iodine, the reduction of iodine. Iodine is... Oh, okay, it's not quite as high as I thought. Here's the reduction of iodine, normally 0.54 volts in our world, but if everyone went up by 1.66, then it would be listed as 2.20 volts. Good. Let's run that a couple more times. Sorry, I'm not very quick at doing the transitions here. If nickel reduction were a potential of 0, pause, data book. Where's our nickel reaction? Here we are. If this were our standard, that would mean we want this line to be 0 volts. What do you do to minus 0.26 to get it up to 0? You add 0.26 volts to it. So that would mean every single listing on this table would be 0.26 volts higher. They are asking about the reduction of barium. Way down here, so this reaction, like all the others, would be increased by 0.26 volts. Sorry, that's from the previous question. Minus 2.91, 285, minus 265, if my mental math is correct. That would be the new number for barium if we lived in a nickel standard world. Not bad, I hope. Pretty easy after you've done a few. Let's see what else they have for us. But first, let me get these cleaned up so we don't have a bunch of confusing notes on our redox table. Okay, last one. If the reduction of fluorine were the reference half cell, pause. The reduction of fluorine is at the very top of our current list, and it's 2.87 volts. If we want that to be 0, we would have to reduce it by 2.87 volts. Well, that would mean we reduce everybody by 2.87 volts, minus 2.87. Everything on the list goes down by 2.87 volts. The question is about what would be the potential for... Oh, trick question. Tell you what, I'm going to do this like there isn't a shortcut, and I'm going to get the answer, and if you're thinking there's a shortcut and there'd be an easier way to figure this out, you're right, and I'll do that at the end. But for starters, the two half reactions they have here would be 2 hydrogen gaining 2 electrons and turning into hydrogen gas, and then we would have lead metal turning to lead 2 and producing 2 electrons. So these are the 2 voltages we need, hydrogen and lead 2. What would they look like in the fluorine world? Well, everybody went down by 2.87 volts, so 0 minus 2.87, hydrogen would be down to minus 2.87 volts. That's the updated number. And lead 2, right here, would be minus 0.13, minus 2.87 would be negative 3 volts. So those would be the numbers in the data book if we were on the fluorine standard. So what would this cell give us? For the hydrogen, we'd have minus 2.87 volts. For lead, the data book would say minus 3, but because this reaction is flipped, we would flip that to plus 3 volts. Then we would add these together and we would get positive 0.13 volts. Okay with that? Do you think there's an easier way to do this one? Because if you do, you're right. And the trick with this is cells do not care what standard we are on. So the power of this battery, a hydrogen-lead battery, shouldn't depend on what our standard is. It should give us 0.13 volts no matter what the standard is. What if we used our regular numbers? Forget about the reduction of fluorine being the reference half cell. What would you get if you just used the numbers out of the data book the way we normally do? Forget all this different standard stuff. If we just said you have a hydrogen lead cell, you would look this up and find 0 for hydrogen, negative 0.13 for lead. So with the normal cell, we'd get 0 volts for the hydrogen. For the lead, we'd find negative 0.13, but because this reaction is flipped, we'd change that to positive 0.13. We would add those together, and we would get 0.13 volts. The same thing we got with the standard changed. Again, chemistry doesn't care what standard you're on, so if you're finding the voltage of a cell, a complete cell, it doesn't matter what you use for your standard. You can use our data book and you'll get the right results. If we make a hydrogen-lead cell and get 0.13 volts, and then aliens from some other world where fluorine is the standard make that same cell with hydrogen and lead, it should have the same power as ours. It should produce the same voltage. Just because we have different data books doesn't mean there's anything different about the chemistry. So changing the standard changes listings in the data book. It changes what the half reactions are rated, but it doesn't have anything to do with the total potential of a cell. For the total potential, you can use any standard you like, and generally we'll go with our data book standard because it's already there. Fair enough?